Yo, it's Bepis. I'm back with another reaction, and today we're going to be checking out something that was recommended to me by my Discord server, which you can join in the description below, by the way. We're going to be looking at what happens if you constantly accelerate by 1G in outer space, because, as you may know, I have a degree in aerospace engineering. However, I don't have a degree in astrophysics, so this is something that's a little beyond my comprehension, but we're going to see what happens.
Imagine you are sitting in a rocket with a special engine able to generate 1G of acceleration forever.
Okay.
But once you turn it on, you can never turn it off.
So when it says 1G of acceleration, does it mean 9.8 meters per second squared is just at your constant acceleration? That's my guess.
Since you're a curious individual without self-preservation instinct, you press it. 1G is not enough to escape our planet, so let's put it into orbit first and then press the button.
Good idea.
At this time, you might think that this is going to be just a boring ride and you are going to spend rest of your life just observing the universe. But at least you still get to enjoy Earth's gravity during your life. But this couldn't be further from the truth. And you are going to experience the oldest light in the universe, visible with your own eyes. And this happens during your lifetime. So on this panel, we depict proper time, which is time you measure directly on your watch. This is the distance you covered, but this distance is measured by the observer on Earth. Because this is what is interesting for us.
Is it like light years?
All the distances in the universe we have measured so far were relative to the Earth. This is the gamma factor relative to the Earth, so it basically represents your speed relative to Earth in a certain way. This is the time an observer on Earth measures on his clock when you are at this location. So it's simply the distance you cover in Earth reference frame divided by your speed. And this is your speed in the percentage of the speed of light. Now let's make the time moving 300 times faster.
Okay. So we're just doing a Kerbal Space Program warp, alright. Do we have like a speedometer or something? I want to see how fast we're moving. Oh, I know it says up there. I'm dumb. I'm sorry. I'm just dumb.
And in roughly 2.5 hours, you reach the moon at roughly 0.03% of the speed of light.
Damn, that is
roughly
fast.
90 kilometers per second. At this speed, we cross the entire radius of the moon in just 19 seconds.
What?
If you look back on Earth with camera,
we've just been going at 9.8 meters per second
and it would be shrinking roughly 0.4 pixels per second. So it would be kinda slow.
Like, that's not a number you think is that high. But I mean, there's no terminal velocity in space like there is on Earth, so I guess that makes sense on why we're going so fast. We're already reaching Mars? In a day?
1 day and 7 hours, we are currently 200,000 kilometers from Mars, moving at the speed of 0.36% of the speed of light.
We're not even a percent of the speed of light.
A second.
And we're already reaching Mars.
If you see Mars 100 pixels large, then it grows at the rate of half a pixel a second. We can also notice that our clock disagrees with the Earth's clock by 1 second.
Right.
So we are starting to really feel the effects of relativity.
Yeah, I was just about to say relativity. Makes sense. I learned that from game theory, by the way, and why Rosalina is so old. That's how I learned a lot of my physics was through game theory. I'll never forget you, Matt Pat.
9 days, 3 billion kilometers from Earth, you reach the last planet of our solar system.
That's
Neptune.
insane, actually.
Sitting at 2.5
9 days,
light, which is roughly 7,700 kilometers per second. At this point, you register more than a minute difference with the clock on Earth. But here I want to pause a little, because this is not the value of the clock on Earth in your reference frame as a traveling observer. It's the value of the clock on Earth that people on Earth measure when you cross the Neptune.
Huh? Huh? I don't know what I don't know what bro meant by that.
And now, 26 days, you finally reach the Voyager 1, the furthest man-made object in the universe.
Yo, what's
Your
good,
speed is
Voyager?
23,000 kilometers
What's good,
a
little
second.
dude?
So
You still got
no
your gold
chance
record
of
on
actually
it?
seeing it. But now
Obviously
you're
it does,
officially the
but
furthest thing humanity
I wonder
has
if anybody
sent
is gonna.
into space.
I still wonder if anyone is gonna actually discover the golden record and figure out how to actually play it, because that's
You
pretty
can start to
insane.
notice that as you go faster and faster, the stars seem to drift towards the center of the direction of your travel, creating this bright pile of stars. This is the effect of aberration and the Doppler shift. After roughly a month later, 51 days into the trip, you start to feel sick, and you notice that the radiation inside the ship has increased. The space is not completely empty. There's roughly 1 million protons per cubic meter in the interstellar space.
Yeah, stars emit a bunch of radiation.
The protons are
They're pretty
hitting the
much
ship
big
with the
nuclear
energies of
furnaces.
9 mega electron volts, which is highly ionizing radiation. But you are prepared, so you deploy some magnetic shielding and continue. And now our ship is
yeah, no
heading
big
into
deal.
interstellar
Cosmic radiation,
space,
one of the biggest
leaving
hazards to
our
space
solar
travel.
system behind.
No biggie. What? 1.5 million times? Oh, okay, sure. We've got to 75% the speed of light in just under a year? What?
And almost 1 light year away from Earth, something happens. It's not anything you could see or experience. It's something that could affect your mental health. This is the time you completely lose contact with your home planet Earth. You can still receive old messages that have already been sent, but any new messages that were sent after this time won't ever reach you. You will never see your children getting older by more than this time.
Bro, I'm not gonna see my chat again?
Disconnected to you.
No.
As long as you keep accelerating.
How am I gonna get my
Special
Twitch
activity, the
subscribers
accelerated
now?
motion corresponds to a hyperbolic trajectory, as you can see on this diagram. On
Right.
this diagram, light takes a straight path at 45-degree angle.
Yeah, and there's a
But there
point
is a
where
clear
it doesn't
asymptote
intersect.
of your curve, and beyond this time,
Right.
no signal can ever reach you.
Interesting.
This is called the Rindler horizon.
I thought it was. I thought I was gonna say the Riddler horizon, like, riddle me this, Batman. How long does it take to travel at the speed of light until you cannot receive a signal from Earth anymore? That's very easy math, Riddler. The curse is foiled again by the Batman.
Now, you can still receive messages, but each message is going to be much further apart from the last one.
Right,
And surely enough, there is a last message you will ever receive in the distant future.
That's morbid. But wait, couldn't messages be sent if they were sent at a different frequency? Or no, if it's going at the speed of light, there is no other frequency. That's right. My bad. I forgot about that. I forgot basic physics for a second. It only took us 4 years to reach
to the closest star,
just about
Proxima Centauri, at a distance of 4.25 light years from Earth.
There's no way it took us 5 years.
The distance is more than 4 light years, yet you covered it in just 2 years and 107 days on your clock. Yet your speed is just 98% of the speed of light. And maybe this is some misunderstanding in special relativity, that we are somehow capped by the speed of light.
So, in reality, over 5 years have passed, but we have aged by 2.5 years, basically. Yeah, relativity is insane.
Speed is just 98% of the speed of light. And maybe this is some misunderstanding in special relativity, that we are somehow capped by the speed of light. But if you have good enough engine, there is nothing stopping you to cover whatever distance you want in small amount of time. So in your lifetime, You could traverse the entire observable universe, provided you have good enough engine.
Right.
The reason is that even though your speed never crosses the speed of light, the length contraction compensates this so the distances are shorter. And at this time we have gamma factor of over 5, meaning that for us, everything is more than 5 times closer than an observer on Earth would measure. Proxima Centauri is a relatively cold star, with a temperature of roughly 3000 Kelvin.
Yeah, no, that's cold.
Category.
Yeah,
but
totally.
This is not what you would see. At your speed, the Doppler shift factor is roughly 10, so you would basically see effective temperature of 30,000 Kelvin, which puts it into a blue star category. Moreover, the intensity of the star changes even more drastically, as it scales with the fourth power of the Doppler factor. This would make the star roughly 10,000 times brighter per unit of solid angle, but since the aberration makes the apparent size of the star smaller, the total received flux of radiation is just roughly 100 times larger. When we talk about radiation, it can sometimes be a little messy. We use terms like radiation intensity and radiation flux. What I mean by flux is how much energy per second is passing through a square meter, and take just the perpendicular component of that.
Okay.
This is a forward-facing flux.
So I'm guessing a magnet shield won't be enough on this kind of thing.
How much a unit of solid angle contributes to this flux. So flux is an integral of this intensity to the spherical angle. When you look at the star, the velocity, the intensity grows as gamma to the power of 4, which is very fast. But the radius shrinks as r over gamma due to aberration, and therefore there is less solid angle that radiates. Therefore the total flux scales just as gamma squared. Moreover, for such a large gamma, the Doppler shift moves the peak of radiation out of the visible range for a star. And therefore, even though the star is 113 times brighter, it's only 54 times brighter in the visible range. But Proxima has the peak well
Where's carbon when you need it, man?
Zero velocity. So with the velocity, the brightness in the visible range grows much faster than the total brightness, as you can see here. And then it slows as the peak moves away from the visible range into ultraviolet. As you pass by, you see the star to dim and move towards the red part of the spectrum as the Doppler effect reverses. Interesting observation is also that you will still see it spherical and not contracted according to Lorentz contraction phenomena. This is the Terrell-Penrose effect, where a combination of length contraction and finite speed of light compensate and make spherical object remain spherical but rotated. As you pass the star, it would appear larger at the same distance than when you were moving towards it due to aberration, but the star would be very dim.
Okay. And we've reached the speed of light in 3, 2...
At this point, all the stars in the universe are concentrated into a small region of space.
Wow.
And around them,
the entire universe
glow starts to appear. This is the cosmic microwave background radiation, but heavily
microwave
the effective temperature of 1500 Kelvin. We are now looking at the oldest light in the universe.
Whoa.
Light emitted in less than 400,000 years after the Big Bang. If the universe was empty, this CMB would be visible even sooner, but it was outshined by the star pile. But at this gamma, the radiation peak of these stars is well beyond the visible range, so the visible flux of stars doesn't grow as much. On the other hand, the radiation peak of CMB is slowly moving towards the visible range. And there is also a lot larger energy density of the CMB photons in the universe compared to the photons emitted by the stars.
Dude, this is so far out of my pay grade. I just do manufacturing and stuff, dude.
The radiation peak approaches the visible range.
This is so far out of my pay grade. But we've only taken 7 years to get here, although like thousands have passed in Earth years. Is this could be the secret to time travel, really.
At this time, The radiation flux of the CMB reached 1,350 watts per meter squared, which is the same flux as we experience from the sun on Earth. So now the whole universe is illuminated as if it was a daylight on Earth.
Wow.
But this star would be kinda different. It wouldn't be a white star, but it would be a very hot blue star with effective temperature of 50,000 Kelvin. The flux in the visible range would
That's at least
be
10
just
times
0.4 watts per meter squared.
the temperature of our sun. What the hell?
Brighter than a full moon. And
Wow.
it would appear kinda bluish. And all this happened in less than 10 years. And you're already 9,000 light years from home. So you didn't left your galaxy yet. But
What?
do you remember our initial problem with proton radiation?
We haven't even left our own
It got
galaxy yet?
significantly worse. Now we are basically inside LHC with each proton having more than 8 tera electron volts. Not even
LHC.
more than LHC actually.
Or
This
LHC.
creates 3.5 terawatts per meter squared.
Yeah, we're pretty much
There is
in a
nothing that could
microwave.
survive this.
We're
This
in
is
a
really
microwave,
good
bro.
end. But it took less than 10 years to travel 9,000 light years.
Holy
How
crap, that's
far could we
insane.
go in our lifetime? And actually,
Oh man,
from
that's
now
gonna be
on,
crazy.
things start to go quite quickly.
Bro used to Dragon
Right now,
Balls to
you're
become
9,000
immortal.
light years from home, and in less than 12 years, you traverse the entire Milky Way galaxy. In 15 years, you
What?
reach the Andromeda galaxy, and in less than 25 years, you reach the end of the observable universe.
20
which is currently 46 billion light years.
That's
away.
nothing!
So as you see, simple 1g of acceleration can get you anywhere. But the universe won't allow you to do this even if you had enough fuel, as this is not an empty space. So now, let's enjoy the whole trip from start to finish again.
Wow. That... Why haven't we tried that 4 missions to Mars? Because that would save so much time. And to the moon, too. Because we won't have enough fuel to pull something like this off, obviously. But we absolutely could. 4 missions to the moon or Mars. It's possible. It would be very hard to maintain. We'd have to get like a infinitely sustainable fuel. And we don't have any electrical engines yet, or like ion powered engines or anything like that. We're not in the Kerbal era yet. But if we figure that out, we'd be going places. Like, you could go to Mars pretty reasonably quickly. Yeah, now we're witnessing a bunch of radiation and stuff. I never got all that good about radiation and the physics behind it. I just know about what it does to the human body and how it prevents us from really taking strides in space travel.
I already uploaded a short video of the trip in the HDR for my members. HDR is kinda important when you wanna display brightness, as the pixels contain not only information about the color, but also about the brightness.
Okay, that's
This gives
actually
you
a pretty good
wider
idea.
range of intensities
That's a
you can
good way to
display.
use a paid
But
subscription.
even with HDR, properly displaying what you would see is still kinda difficult, as you have to think of saturation threshold of your own eyes.
I'll
But
go into
this
that in a second.
changes depending on how wide your pupil is. And I think that
Of
the video I
course.
posted is kinda overly bright. So I will probably post another video with corrected intensities for my members. And
Right.
if you are my Patreon member, I will share the link with you. Just send me a message there, and I will send it to you when it's finished. See you next time.
Wow, dude. I didn't know it would take that little amount of acceleration in the grand scheme of things, like 9.8 meters per second. Yeah, that's what we experience on Earth every day. So hypothetically, by undergoing this acceleration, a good chunk of us have already traveled, I'd say, what, to Andromeda? If we were accelerating in a straight line from Earth instead of towards it? If that makes sense. Damn, dude. Astrophysics really is something. I want to do more of these where I try to wrap my brain around things about space that I didn't pick up with an aerospace engineering degree. Because again, as I mentioned before, I only did manufacturing related stuff and mechanics. I focus more on building spacecraft and rockets and the materials needed for space operations, but this is really cool. Of course, if you want to see me do any more reactions like this, you can go to my Discord server or just drop a comment here below. And if you like what you saw, you can join the Bepis crew by leaving a like or a subscribe. And let me know what you would do during your time on a constantly moving ship. Like, how would you get the time to go by? You know, would you bring any video games? I would personally bring Tomodachi Life or, you know, Dokkan Battle, because those two games make time just go way by. But with all that being said, thank you so much for watching, and as always, stay frosty, y'all.